Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. It's a continuation of a series on graphing the sine and the cosine function as if you've never seen it before. And that's good because you want to be able to kind of approach this material from a fresh perspective. So let's go ahead and talk about the new topics. You should have already covered the base graphs for the sine and the cosine, and amplitude and reflections, midline, and vertical shifts. And this is the next in that series. So let's focus in this video on the period of a trig function, how that relates to the graph of the trig function. By the way, we happen to know from our prerequisite material that if you have something like, f of bx, that looks just like the function f of x, except it's been stretched or compressed, horizontally, that's kind of the critical part, by a factor of 1 over b. That should be from your prerequisite material. When you're dealing with trigonometric functions, however, it's much easier to do this using a different method. So let's go ahead and explore that here. The period of sine of bx and the cosine of bx. Well, let's see. The period for y equals a sine of bx plus d and y equals a cosine of bx plus d is 2 pi over b. And why is that the case? Well, here's the proof. The period of sine of theta, and by the way, I could have called this cosine of theta, it's the same proof either way. The period of the sine of theta is 2 pi. That is, it goes through one full cycle on the interval 0 to 2 pi. However, in this case, our angle is not theta, but instead our angle is bx. So if we allow theta to equal bx, then we have the interval bx is between 0 and 2 pi. And this will imply that if you divide everything by b, and b is positive, it doesn't have to be positive, but we're going to assume that b is positive here. So assuming without loss of generality that b is positive, we have that the sine of bx actually goes through a full cycle from 0 to 2 pi over b. Again, that's assuming without loss of generality that b is greater than 0. That's what this means, without loss of generality. It just means that if b were negative, in order to divide both sides by b, yes, you'd switch signs, all that fun stuff, but it still would give you a period of 2 pi over b. So again, a full cycle. Maybe I should write that down. So thus a full cycle of sine of bx occurs on 0 to 2 pi over b, hence the period of sine of bx is 2 pi over b. So that is a really very nice statement. It's a very, very nice way to know how long it takes for your sine or cosine. I could do this whole entire proof with the cosine, it's the same proof. It's a good way to know how long it takes your sine or cosine to get through a complete cycle. Also note that the language I'm using here, every single time we increase or move forward in this video series, we just add another component. So we started with this a, and then we went to the plus d, and now we have included a b as well. So each step of the way, we're adding another set of complications to this. So the first part here, let's just go ahead and state the period of this function. We're not going to graph it. We're just going to state the period of it. Now, if you are one of those people who like to letter everything, a here is equal to 2, b here is equal to 3, and d here is equal to 1. I do not normally like to do that, mainly because it's too algorithmic for me. I really like a natural understanding of how this goes. So anyhow, the period of this function by our theorem is going to be 2 pi over the b, or 2 pi over 3. So that's how long it would take this cosine to go through a complete cycle. It's 1/3 of its normal 2 pi. Remember, the normal period for a cosine is 2 pi, but this is actually 1/3 of that, which is the reciprocal of that coefficient on x. All right, so that's just answering the first question. Likewise, we could do the same thing for a sine function. All the other numbers don't matter here when you're asked to find the period of a function, of a trig function, that is. So the period in this case, again, it's just 2 pi over the coefficient of x, which is 1/3. If you multiply numerator and denominator by 3, you get 6 pi. So it takes 6 pi, a length of 6 pi along the x-axis to complete a full cycle of the sine function in this case. So we're essentially elongating this sine function. Now, rather than start with graphing by hand, I want to showcase this because it does make a very impactful difference to see this in action. Going back to our Desmos example, I just typed in a sine of bx plus d just to remind you that that's what we were doing before. I'll just add a slider to all, but I'll set a to be 1 and d to be 0 because I don't want to shift things up for this example. And b is 1 right now. Now, as we increase b, and let me go ahead and shrink this down a little bit so we have a better view here. As we increase b, it actually decreases, or maybe I should say, as you increase b, it increases or decreases the period. It increases the number of wiggles. And in fact, let's just keep an eye. Let's go to pi over 2. Yeah, let's take a look at pi over 2. Or maybe better yet, let's take it from 0 to 2 pi. If I started this at 1, so b is equal to 1 here. From 0 to 2 pi, that's what I meant to say, 0 to 2 pi, we get a full cycle of the sine curve, right? Well, let's suppose, let me step by 1 here. Let's suppose instead we go to b equals 2. Now notice what happens. We go through 1, 2 full cycles from 0 to 2 pi. If we go to 3, b equals 3, we go 1, 2, 3 full cycles from 0 to 2 pi. And you can keep doing that all day long. In fact, that coefficient b right here tells you how many cycles you have between 0 and 2 pi. That's kind of a neat way to think about it. Now, I'm going to turn off the step size. We'll step by maybe a size of 0.1. And I'll drag that down. Notice as the numbers get smaller, it's like a slinky that you're pulling out wider and wider. So it gets more and more elongated. So for b equals a half, it only goes through half a cycle between 0 and 2 pi. You'd have to go all the way out to 4 pi to finish out the cycle of the sine curve. So there is a good visual of how b affects the graph. Again, increase b, and it will increase the number of cycles per unit time. Decrease b, and it will pull it out like a slinky. Okay, and if b is negative, by the way, it just flips it about the y-axis. The reason why I wanted to talk about that or show that in Desmos before we graph by hand is because to graph by hand requires a little bit of a nuance here. We have to know a little more detail. So let's go ahead and define something. Now, these are not official definitions. These are my definitions. But most instructors will kind of adhere to the same style of definitions. They might not call them the same thing as me, but they're the same thing. So the key points for the base, sine, and cosine functions occur at x equals 0, x equals pi over 2, x equals pi, 3 pi over 2, and 2 pi. Those are the kind of the what are considered the critical numbers for these curves, because that's what you're labeling when you graph out the sine curve, right? If you graph out the sine curve, normally you say, oh, it starts at 0, ends at 2 pi, halfway through is pi, halfway to that is pi over 2, and add a pi over 2 right here, and you have 3 pi over 2. Notice those are the critical numbers. So those are the ones you would always label. However, things get changed if you have a change in the period for the function. So those numbers are going to slightly change. So we need to talk about them with the common language. So those are called the key points. The first of these is called the initial point. So x equals 0 is the initial point. And the distance between any two consecutive key points we'll call the step size. Notice the distance between any two consecutive points, in this case, is pi over 2. Step size of pi over 2. Add another pi over 2. And yet again, add another pi over 2. So the step size here, the normal step size, is pi over 2. How do you compute the step size? Well, the step size for the sine and the cosine is the period over 4. You're dicing up that interval that goes from 0 to 2 pi into 4 pieces. So our period normally is 2 pi. If you divide that by 4, you get pi over 2. And it actually cuts this interval into 5 sections. 4 sections. I apologize. I'm 5 edge points, 4 sections. 1, 2, 3, 4 sections. So anyhow, you cut it into 4 sections because, well, that's what you need to graph either the sine or the cosine, is 4 subsections. One to give you the maximum, then you cross. One to get you to the minimum, then you cross. That's if it's the sine. If it's a cosine, it's 1. You start high, 1 to cross, 1 to go low, 1 to cross, 1 to go high. So these are the key points. All right. And so this is the formula we're going to use to compute our step size. So let's go ahead and start graphing by hand. State the period and the step size of y equals the cosine of 3x, and then graph this function by hand, labeling all key points. Well, let's see. The period is going to be 2 pi over the coefficient of x. The coefficient of x here is 3. So it's 2 pi over 3. That's the period of this function. The step size is going to be the period over 4. We're slicing up that period into 4 chunks. So it's 2 pi over 3 divided by 4, or in other words, 2 pi over 12, which is pi over 6. Now that we have that, we can graph the function. Now, I'm not asking you to state the midline yet. So I'm just really focusing on period and stuff like that here. But really, I'm just going to go ahead and graph the midline. So let me use green to graph the midline. Turns out, since this function's not being lifted or lowered, the midline is the x-axis. So I'll just go ahead and relabel that the x-axis here. It's just the x-axis. And I'll start my cosine curve. Notice it's a positive cosine, so I just graph the positive cosine. Try to be somewhat clean about this graph. Again, I'm a stickler for that. And now I'm going to label each of these points. The starting point here is 0. That will change in the future, but for right now, in this specific video, we are not going to shift left or right. We're going to stick with a normal curve starting at x equals 0. And the period is 2 pi over 3. Now, I could totally write 2 pi over 3 right here, but that's a bad habit. It's actually really bad to do that. So instead, I'm going to start at 0, and I'm going to add the step size to get to the next point. So that I'm going to add the step size to get to the next point. So that's pi over 6. Then I'm going to do it again. Add the step size to get to the next point. So that's 2 pi over 6. And then I'm going to add, again, the step size to get to the next point in line, 3 pi over 6. And then finally, the fourth point, I'm going to again add another step size to get to 4 pi over 6. Now, notice I didn't reduce these numbers because, well, there really truthfully is no reason to. And in the long run, it's better to not reduce those numbers when you're graphing here for trig functions. So just leave them like that. That's perfectly fine. But notice that this number is 2 pi over 3. So we went from 0 to 2 pi over 3, which is actually the period. That does work out. So, but again, very dangerous if you say, oh, I'll start with 0 and I'll end with 2 pi over 3. It's very dangerous because when you start shifting left or right, you're not going to end at 2 pi over 3. You're going to have a distance here of 2 pi over 3. But because you're going to be shifted where your starting point is no longer 0 eventually, it won't end at 2 pi over 3. Okay, now we're just going to finish this out. I'll draw in the y-axis, which is right where x is equal to 0. And I'll label the amplitude here. So our midline is the x-axis. Our amplitude actually is 1. That's a coefficient of 1 on there. So I know that this is a height of 1, the maximum is, and the minimum has a depth of -1. And that's a single cycle of this function. I could continue on if I wanted to, but I'm not going to. But notice I have all my key points labeled. I actually have graphed the axes. I've stated what the maximum and the minimum are. Yeah, this is a good, decent graph of this. I've also stated the step size. That's kind of critical. So let's try that again. Completely different example. Again, very nice example because I'm not really I don't really have an amplitude other than 1. So the amplitude is equal to 1. Well, the A is equal to 1. And D, which is the vertical shift or the midline, is equal to 0. So we're really not moving anything or stretching anything vertically. I just want to get us used to the period of a function first. So we'll pull things together later. So the period of this function is going to be 2 pi over the coefficient of x, which is 1/3. That is going to be a 6 pi. And the step size is equal to the period divided by 4. And that's going to be 6 pi over 4. The step size here is 3 pi over 2. It reduces down. All right. Well, there's no horizontal shift or vertical shift, actually, either or. So let's go ahead and graph this function. Since there's not a horizontal shift, vertical shift, I don't have to worry about the midline being lifted off of the x-axis. So my midline is the x-axis. I'll just graph a standard sine curve, trying to be careful. Now, some people will say, wait, shouldn't I make that stretched out because it's a stretched out, the period is like 3 times more than the regular period? No, you don't have to actually stretch it out because you're going to label everything. So the scale will stretch things out for you. I start at the initial value, which for now is just going to be 0. And I go by the step size. I'm going to add 3 pi over 2 to get to this point. The next critical number or key point will occur at another 3 pi over 2, which is 6 pi over 2 now. And then you add another 3 pi over 2 to get to the next key point. And then finally, the last 3 pi over 2 that you're adding, you get to the final key point. By the way, 12 pi over 2 is 6 pi. We went from 0 to 6 pi. That's actually the full period of the sine curve. And then just draw in the y-axis. And make sure that once you draw in the y-axis, which I'll label right there, that you go ahead and label the maximum and minimum values for that function. So the maximum value is going to be 1. The minimum value for the sine curve is a -1 because, again, our amplitude actually is 1. So it's not really vertically stretched at all. All right. Oh, and if you wanted to, if your instructor requires it, you could showcase that this goes on forever. It does. It's understood that it does. All right. So that does it, honestly, for this material. And then in the next section, we're going to do the final type of transformation, which is a phase shift. And once we're done with phase shift, there'll be another video putting everything together all at once and kind of giving you a nice clean way of doing all this graphing.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.